Hello. Today I'll talk about type bounds for adversarially robust streams and sliding windows via distance estimators. This is work by David Woodruff and Samson Zhou. Now the first model we'll consider today is the stream model, in which the input is elements of an underlying dataset S, which arrives sequentially, and the output is to evaluate or approximate some given function using space sublinear in the size M of the input S. For example, if we have the sequence of bits that appear at the bottom of the screen, then the number of ones in the stream is going to be 5. So what problems do people consider in the streaming model? One frequently studied problem is the problem of heavy hitters, in which you're given a set S of M elements from the universe of size n, and we let Fi be the frequency of element I, which is how often it appears. Then the stream that appears in the middle of the screen induces the frequency vector 5, 3, 1, 0. And for example, F1 is equal to 5 because 1 appears 5 times in the stream. Now in this problem, we let L2 be the norm of the frequency vector, which is the square root of the sum of the squares of the coordinates in the frequency vector. And the goal is to output the elements I such that Fi is at least an epsilon fraction of L2. And we don't want to output any elements j such that Fj is less than, let's say, epsilon over 16 times L2. A rather commonly studied problem is the frequency moments problem, where Fp is the frequency moment of the vector, and it's equal to the sum of the pth powers of the coordinates of the vector. And given an accuracy parameter epsilon, the goal is to output a 1 plus epsilon approximation to Fp. Another commonly studied problem is the distinct elements problem, in which the goal is to output the number of times a unique element appears in the stream. In particular, if we're given an accuracy parameter epsilon, we would like to output a 1 plus epsilon approximation to F0. And there's been a long work of progress on these problems. And the main takeaway is that these problems can mostly be done in 1 over epsilon squared space. And outside of Fp for p bigger than 2, the problems can also be done in polylog space, where n is the size of the underlying frequency vector. The next model we'll discuss is the adversarially rebustering model, in which the elements of an underlying dataset S arrive sequentially and adversarially. And again, the goal is to output an evaluation or an approximation of a given function using space sublinear in the size M of the input. But the key is that the input now is generated adversarially. So suppose we have a sequence of bits again, and let's suppose that the adversary first generates a bit 1, and our algorithm outputs 1 because that's the number of bits it's seen so far. Now, seeing the output of the algorithm, the adversary chooses another bit to input in the stream. And let's suppose the next bit it chooses is 0. And so the algorithm outputs that it's seen 1 bit so far, rather 1, 1 in the sequence of 2 bits. Now the adversary outputs a third bit. This is input to the algorithm, which has now seen 2 bits that are 1 in the stream. Finally, let's suppose that the algorithm outputs another 0 and gives that as input to the algorithm. And the algorithm now incorrectly sees 3 bits of 1s in the stream. In this case, the adversary has fooled the honest algorithm. So in this case, we call the input adversarially robust. But the premise is that future queries may depend on previous queries, even if the input isn't quite adversarially generated. And in some recent work by Ben Eliezer et al., it was shown that 1 plus epsilon robust algorithms were given for a number of these frequently studied streaming problems. And the overhead in terms of the epsilon dependencies was 1 over epsilon cubed. And so the main takeaway from this paper is that there's a general framework that loses almost nothing in n, and only 1 over epsilon factors in the approximation parameter epsilon. But unfortunately, epsilon can be quite large in the settings of big data that we studied today. In fact, 1 over epsilon can actually be larger than log n, so we should really care about the epsilon factors. And this is motivation for the follow-up work by Heston et al., who used differential privacy to give space algorithms that have a dependency of 1 over epsilon to the 2.5. So they do lose log factors over the previous work, but the main takeaway of this paper is that an entire 1 over epsilon loss is not necessary. Our work shows that we can actually get space bounds for these algorithms that use dependency 1 over epsilon squared. And so our main message is that no losses are necessary at all in terms of the higher order dependencies. So in summary, we lose neither log factors nor epsilon factors for all these different problems in the adversarially robust model. But now the title also talks about the sliding window model. And in this model, we have, again, an underlying data set S, which arrives sequentially. But now only the M most recent updates form the underlying data set S. And the entire stream can be much longer than S. Sorry, longer than M updates. For example, let's suppose that we have an active window of 8 bits. And now let's suppose that we see bits 1 at a time. So until we see 8 bits, the entire data set is just the entire sequence of bits. But once we see the 9th bit, then the first bit expires, and our data set moves to be the most recent 8 bits. And this process continues when the 10th bit arrives and so forth. But the tricky part is that we don't know which bit expires. We know the time for which the bit expires, but we don't know its actual value and lets us store all the bits entirely, but that defeats the purpose of using sublinear space. So the main obstacle in the sliding window model is that a lot of information expires implicitly. And what's known in the sliding window model? Well, in terms of F0 and L2 heavy hitters, there are algorithms that get space dependency 1 over epsilon squared. But for a large number of other problems that are important, the space dependency there is going to be 1 over epsilon cubed for Fp between P between 0 and 1. And it's even worse for P bigger than 1. So in the sliding window model, what's known by this framework of Braverman and Ostrovsky is that they provide a general framework that loses nothing n, but they do lose 1 over epsilon factors. And our results are that for these problems in the sliding window model, 1 over epsilon losses are also not necessary. So in summary, we get no losses in 1 over epsilon for either the sliding window model or the adversarially robust streaming model. And as a quick description of what we do, let's first go over a warm-up algorithm, which is known as the famous AMS F2 algorithm. This is due to Alan, Matthias, and Chegedy. So in this algorithm, the goal is to estimate F2. And generally, a sign vector of length n is generated. We'll call that S. And as the stream progresses, a counter for Z is stored, where Z is the inner product of S and F. And now at the end of the stream, we'll have Z, and we'll consider Z squared. Now it can be shown that the expectation of Z squared is exactly F2, and the variance is going to be F2 squared. So roughly, if we take the mean of 1 over epsilon squared inner products, then it suffices for 1 plus epsilon approximation. But if the algorithm were adversarially generated, one can choose the inputs so that the signs of the frequency vector, of the sign vector, all align with the frequency vector. And in particular, we can force Z to be M and Z squared to be M squared deterministically, but M squared is obviously not going to be F2 of the stream. So in this attack, what happened is that the randomness of the algorithm is not independent of the input. And indeed, there have been known attacks on linear sketches that show that linear sketches in general are not robust to adversarial attacks. Obviously, there's been previous work on these adversarially robust streams. So what did they do? Well, the key is that in the insertion-only model, deletions are needed to perform this attack, and deletions cannot be done in the insertion-only model. And similar lower bounds are known for the streaming or for the sliding window model, in which if you allow deletions, then the model requires linear space. So for both these models, we'll assume insertion-only updates for the rest of the talk. And now the question is, how do the previous results work? So the previous framework by Ben Alex et al. Introduced a sketch switching framework. And the idea is that they start many instances of the streaming algorithm at the beginning. They use an instance of the algorithm, but they freeze the output. And each time the next instance has value 1 plus epsilon more than the frozen output, then they freeze the next instance and use its output instead. But perhaps this is best illustrated by an example. So let's consider the previous problem where we would like to approximate within a factor of 2 the number of ones in a stream of bits. And let's suppose that we have 4 algorithms running, the red, yellow, purple, and blue algorithms. And we've chosen to output whatever the red algorithm outputs at the first bit of the stream. So we see a 1. And at this point, all 4 algorithms will output a 1. But we freeze the red algorithm, so it will always output 1 forevermore afterwards. Now we see another bit, and nothing has changed for any of the 4 algorithms. And let's suppose we see a third bit. In this case, it's a 1. Now the red algorithm will still output a 1 because it's frozen forever. But the other 3 algorithms have now seen 2 1s in the entire sequence of bits. And so they will output 2. And if we want a 2 approximation, then 2, the output of the yellow algorithm, is no longer within a factor of 2-ish of the output of the red algorithm. So what we'll do is that we'll switch to the yellow algorithm and we'll freeze that instead. So now we'll keep outputting 2 because that's what the yellow algorithm outputs, but we'll freeze it for a while. So suppose we see more bits of the stream. Again, the red and the yellow outputs are now frozen, but the other 2 algorithms are free to be updated. And at some point, the purple algorithm will have seen 4 1s. And now the point is that the output of the purple algorithm and the yellow algorithm are a factor of 2 apart. So we switch to the purple algorithm and we freeze it. And this will continue for the rest of the stream. So let's suppose at the end of the stream, we've chosen to select the purple output as the entire output of the algorithm. It will have seen 4 1s in this particular stream. But because we have not switched to the blue algorithm, then we know that the output, the entire number of 1s in the stream, is within a factor of 2 of the purple algorithm. In particular, there are 7 1s in the stream. 7 is less than 8. And we output 4, which is a 2 approximation to 7. Okay, so in summary, sketch switching for a robust algorithm uses 1 over epsilon squared space each time fp increases by a 1 plus epsilon factor. And the function will increase roughly 1 over epsilon. There are some log factors there, but 1 over epsilon times. And the smooth histogram actually has similar ideas. The question is, do we really need to pay 1 over epsilon squared space each time fp increases by a factor of 1 plus epsilon? For example, let's consider 2 frequency vectors, u and u plus v. And let's consider how far apart the fp moment of u and u plus v are. So we have that their difference is just going to be, let's suppose that it's epsilon times fp of u. Let's suppose that v has not contributed much to the entire frequency moment. And the idea is that if their difference is only epsilon times the pth moment of u, then we really need only a constant factor approximation to this difference. So suppose we want the pth moment of u plus v. We can decompose this into the difference of the pth moments of u plus v and u plus the pth moment of u. And now let's suppose we have a good approximation to the pth moment of u, and we just want a good approximation to the difference. We can similarly write this in terms of breaking down V into multiple parts. So previously we had just one vector V, but now we break up V into B parts. And we can again write the moment of U plus V as a difference plus the moment of U. And now we can expand this using a telescoping sum. And recall that V is equal to the sum of the vectors V1 to VB. And we have this large sum of differences. But the point is that we can set each difference to be exponentially decreasing. So the idea is that the Bth difference will be roughly 1/2 to the B times the Pth moment of U. So the first difference here is tiny. The second difference is a bit larger, and so forth. And now the point is that if the difference is tiny, then we can afford to have a crude approximation to this difference. So pictorially, now we have that the vector V1 contributes a much larger mass than the vector of V2, whereas previously the vectors V1 and V2 roughly contribute equal values of mass. Now we can look at our second idea, which is the granularity change. And the point is that since each of these differences are exponentially decreasing, we just need a cruder approximation to each of these differences. And the hope is to use less space for each of these cruder approximations. And so our main framework is that we use a number of algorithms that simultaneously run for each granularity. And the hope is that we can use much less space for a much cruder granularity. But on the other hand, we do need roughly 2 to the B instances for a small granularity. So we can take the sum and take it over all B. And since it's a geometric sum, we can show that the total space is roughly 1/epsilon² in terms of the epsilon dependencies. And this is the intuition. It's not quite formal, but it's the correct intuition for our paper. Now, the main point so far is that if we have a difference that's quite small, does there actually exist an algorithm that approximates the difference and uses much less space? Again, because the difference is small, we can afford a cruder approximation. And thus we define what's called a difference estimator, where if the difference of the Pth moment of U plus V and the Pth moment of U is equal or roughly upper bounded by gamma times the Pth moment of U, we would like to output an estimate to the difference with additive approximation epsilon times the Pth moment of U. And generally, this can be challenging because F is nonlinear. And can also be challenging because constant factor approximations to each of these individual terms do not give an additive epsilon approximation. But if we use an 1 plus epsilon approximation to each of these terms, the space might be too large. So we have to balance both the space usage and the approximation guarantee here. Our results show that we get difference estimators that use space dependency gamma for each of these functions that we're interested in. So we have space difference estimators for F0, for FP moment estimation for P between 0 and 2, and integer P larger than 2. And note the point here is that gamma is roughly how far apart these the difference estimator is. So if the difference estimator corresponds to a smaller difference, namely if gamma is smaller, then the space usage for these terms is smaller. And this is the key property that provides the space accuracy trade-off that we want from our difference estimators. So in summary, we provide a new framework for streaming algorithms. We use two concepts called sketch stitching and granularity change. And in our granularity change, because we want to have algorithms that use less space for cruder granularities, we introduce the concept of difference estimators to afford this. And surprisingly, this works for both the adversarially robust model and the sliding window model. Now, before I conclude my talk, I'd like to go through some future directions. And the first question is that the difference estimator concept is relatively novel, but it seems quite general. So there could be potentially a number of other applications for difference estimators. We also haven't explored the tight bounds for these difference estimators, so it's not known if we can get even a better approximation algorithms in terms of the lower order costs. As I mentioned previously, the difference estimators consider general p bigger than 2. We would like general p bigger than 2, but we only obtain integer p bigger than 2. Finally, another open question is what other adversarially robust algorithms there are. Thank you.